water. We're going to have to do it for methane and see what we get for methane. That's just for water. That's why that number didn't match. Okay, so that's the theory behind it. This is a theoretical way. Now, when chemical reactions proceed, all of the atoms don't first fly apart and all the atoms come together again. But for modeling purposes, and because of the way thermodynamics works, this is a good estimate of bond energies. Everything is kind of happening at once, really. The molecules are colliding with each other, and as something's breaking, something's forming, and it's a way more complicated process, but we can break it down like this to get a good estimate of what the heat of reaction should be. And there's actually a table with all of these bond energies in it, so you can work any problem this way. All you have to do is figure out, what bonds, and in order to figure out what bonds, of course, you have to be able to do Lewis structures. That's another reason why Lewis structures are important. But the way it works is like an H single bond is, the bond energy is 436 kilojoules per mole. See, the units are kilojoules per mole here. Carbon bond, single bond is 356. Down here you've got multiple bonds. Carbon-carbon double bond, 598. Carbon-carbon triple bond, 813. See, the single bonds are of lower energy than the double and triple bonds. All right, so you can see how to use that table. If I said what's the bond energy of an OH bond or an HO bond, find hydrogen, find oxygen, go across, and you'd find 467 kilojoules per mole. So you can use that table to predict heats of reaction. Sometimes heats of reactions are called enthalpies of reactions. Enthalpy of reaction and heat of reaction. Enthalpy is sort of the fancy thermodynamics term for heat of reaction. So let's go ahead and do it here for methane then, and see what we get when you estimate it for methane. It's use bond energies to calculate the enthalpy of reaction of methane. So first of all, you have to correctly write down the chemical equation for the combustion of methane. And in this case, is the reaction written correctly? It's not balanced. So before you can do this, you have to make sure you have a balanced chemical equation. And so it's 1, 1, it's 2 of these, and it's 2 waters. Okay, so now the chemical equation is balanced. And so first make sure it's balanced. Check, write down your equation, make sure it's balanced. Then to figure out what bonds are being made and what bonds are being broken, you have to write down all the Lewis structures. Okay, Lewis structures. And in this example, the Lewis structures have been done for you right down here in this table. Okay, there's all your Lewis structures. You look at the Lewis structure and you say, okay, how many bonds are in this particular molecule? There's 4 CH bonds, and I have 1 mole in this chemical reaction because it's 1 mole plus 2 moles gives 1 mole plus 2 moles. And so the total number of moles of bonds is going to be 4 bonds times 1 mole of that particular molecule in this particular chemical change. So it's going to be 4 bonds, and they're breaking. So since the bonds are breaking, that's going to be an endothermic change, and so it's going to be a positive value. And if you look up on the table for the CH bond, it's 416 kilojoules per mole. Since you have 4 moles of them, you multiply 4 times 416 to get a total energy input to break all of those bonds, and 1 mole of those molecules is 1664 kilojoules. Go through the same process for oxygen. There's only 1 OO double bond, but there's 2 moles of it in this balanced chemical equation. So you have to have 2 times the double bond right here. It's breaking, so it's an absorption. It's 498 per each one. You've got 2 of them, so that's going to be a total of 996. Then you go through the same process for the products. In this case, you're making bonds, so whenever you make a bond, energy is released. And so it's a release of 803 per mole, 467 per mole. These numbers you get from the table that I just showed you. And then you multiply by the number of moles based on the balanced chemical equation and the Lewis structure, and this is the number you get. And so when you add all of those numbers up, the positives and the negatives, the overall change in energy is negative 814 kilojoules per mole of this methane. So the reaction is giving off 814 kilojoules, so that tells you that it's an exothermic change, and that number is very close to the determined number, experimentally determined value from this table. It's at 802, negative 802.3. That's the experimentally determined value. This is the theoretically determined value, so it's very, very close. And in both cases, it agrees that it's going to be an exothermic reaction. So rather than run a calorimetry experiment, a lot of times a chemist will do a quick and dirty calculation like this to determine if they can predict if their reaction is going to be exothermic or endothermic. Okay.